Welcome to session 3, friends. Enough of R, because whatever theory we are going to discuss, we will execute a corresponding R code to see how the results would surface. So it's not that this is end of R, this is beginning of R. Anyways, you got a good exposure to R, how to upload the data sets, how to deal with the data set and things like that. So now is the time that we enter into the statistical analysis, right? We will complete the statistical analysis. We are going to complete the linear regression. We are going to build predictive modeling, predictive models, post which we are going to do data mining unsupervised, and then forecasting followed by data mining supervised. And in between somewhere, I'm going to plug in Tableau visualization. So these are the bunch of things which are scheduled to be completed over the next 1 month or so. Let us continue with this session, and this session would primarily deal with statistical analysis. We are going to start right from the basics, assuming that you guys have absolutely no exposure towards statistical analysis. So few of you all might feel that these concepts are mundane, but in the interest of everyone else, I would request you to just, be a little patient. Here we go. This is the course agenda at a broad level. We'll be discussing about what are the various data types, what do you mean by a random variable, what is probability distribution, right? And then we're going to get into descriptive statistics, graphical summary or graphical representation there, skewness kurtosis, normal distribution, probability calculation for normal distribution. This distribution called normal distribution is going to be the most important distribution in the entire statistical world. This is the most important distribution. We will discuss about normal quartile plot or QQ plot, and we are going to look into statistical inference using SRS, simple random sampling, and finally we are going to look at central limit theorem, not at the depth, but we will just try to get the glimpse of what central limit theorem is all about. Most of these concepts which we're going to discuss now might be dated back to your 10th standard or your +2 or at most your graduation first year or second year, right? So these are the kind of concepts that we are going to discuss now. First come first, let us discuss about the basics. Data types. Broadly speaking, we have 4 data types: nominal, ordinal, interval, and ratio. What do you mean by nominal? Nominal means they are merely labels, names of people, for example. No further information can be gleaned from this. Example is Coke and Pepsi. Let me select the highlighter, laser pointer, right. There is another corresponding example which I have listed here, nominal. If you have seen running race, people are assigned few numbers, right? They have their jersey numbers and things like that. Those numbers on their own hold no value at all, absolutely. And if you have nominal data, you can perform only these 3 calculations. One is mode, frequencies, and percentages. We will get to what do we mean by mode and things like that in a while. The second thing is ordinal. As the name specifies, you're ordering the things. You're placing the things in an order. That is ordinal. It conveys only up to preference information, direction alone. It doesn't quantify, but it will tell what do you prefer. For example, I prefer Coke to Pepsi. That's it. By what number, on a scale of 1 to 10, how much do I prefer Coke to Pepsi? That information is not available in ordinal scale. For example, or let us look into another example here, ordinal, rank order of winners. Obviously, if it's a running race, people will win and they will be placed in the order, right? So you're just saying that, hey, one person got first place, second place, and third place. However, I'm not mentioning here on how much time they have taken to complete the race or how well they have performed. I'm not mentioning that. I'm just telling that these are the people who got first, second, and third place respectively. Order, ordinal order. Now, if you have ordinal scale, you can perform median, right? This is additional calculation that you can perform, and a few of the statistical analysis you can probably perform. Let us look into the third data type, which is called as interval scale. Here, I'm conveying the magnitude. For example, if I say I prefer Coke to Pepsi, I'm not sure how much you prefer. That information is not available. However, in the interval scale, you would be provided with that additional information. I rate Coke a 7 and Pepsi a 4 on a scale of 10. Now it makes sense that there's a huge difference on how much you like Pepsi in comparison to, how much you like Coke in comparison to Pepsi. Look at the corresponding running race example here, interval scale. Performance rating on a 1 to 10 scale, right? Here you have 8.2, 9.1, 9.6. So you know for a fact that the person who has got the first position is far ahead of the race. The second person is just behind the race by 0.5. The difference between these two is 0.5. It's a scale here, but I would request you to consider this as seconds in a 100-meter race. Seconds doesn't make sense. Sorry, forget that, because it should have been the other way around. Anyways, so this third person on a scale of 0 to 10, 10 being the maximum or the highest performance one can achieve, the third position person is rated as 8.2. And then comes your ratio scale. And even before that, look at this. If something is an interval scale, you can calculate the mean of the data set, average. You can calculate the variance, standard deviation. And most of the statistical analysis can be performed if something is interval scale. And we have the ratio scale here. This is the last scale. It conveys information on an absolute scale. Time to finish in seconds. Here is the information, right? Now this is good information provided. So person 3 has taken 15.2 seconds. Person 2 has taken 14.1. And the first position was held by a person who completed the race in 13.4 seconds. If you take the Coke and Pepsi example, you paid 11 rupees for Coke and 12 rupees for Pepsi. If you forget these data types, right, nothing to worry, absolutely. However, you need to know for a fact that if you cannot find out mean and median of a data set, it is called as nominal data. If you cannot find out mean and median of a data set, it is nominal data. If you cannot find out mean of a data set, however, if you can find out median, that is called as ordinal data type. Then comes the interval data type. The only difference between interval and ratio is that if you take ratio of the numbers, it will make sense for ratio scale, for ratio data type. For example, if I say 7 divided by 4 would be approximately 1 point something. It doesn't make sense for me, right? Does it make sense? If I take ratio of the ratings which you provide, it really doesn't make sense for me. All right, so these are the data types. I'm assuming that you might be having few understanding gaps here, but if you do not understand what a data type means by reading a statement, I would request you to go with the statistics. If you cannot find out mean and median, it's nominal. If you can find out median but not the mean, then it's ordinal. If you can find out the mean and ratio of the numbers, that's ratio data type. And obviously, if you cannot find out the ratio of the number, it's called as interval. Simple. Now we have this concept of random variable. What is a random variable? This describes the probabilities for an uncertain future numerical outcome of a random process. Now let me ask you this question. If I flip a coin, what are the possible outcomes? Head or a tail? Head or a tail? There are two possible outcomes. One is head, another thing is tail. Now I'm giving this a name called as X. I'm assigning all the variables or all the possible outcomes to this variable X. Remember, this is your capital X that I've written. Within that capital X, whatever outcome that is possible would be represented using small x, x1, x2, x3, so on and so forth. Very, very important. The capital alphabets and the small alphabets within statistics is extremely important. All right. Now, say there's a random variable x that is outcome of rolling a dice. If I roll a dice, what are the possible outcomes that one can expect? What is that, Monica? Six? Six possible outcomes. What are those? What are those six possible outcomes? One, two, three, four, five, and six. These six possible outcomes of this variable x are represented using x1, x2, x3, x4, x5, and x6. If I flip a coin once, would I get heads always? Would I get a head always? No. Can I get a head? That's my follow-up question. Can I get a head if I flip a coin once? Yes. What is the probability associated with that? What is the chance that I get a head if I toss? 50%, right? That is the basic definition of random variable. Random variable describes the probabilities or chance for an uncertain future numerical outcome. When I ask you, if I flip a coin, what could the possible outcome be? You were uncertain about the future outcome. And when I ask you on, can it be a head? You told yes. When I ask you a follow-up question on what could the possible probability or chance be, you told it's 50%. So you have told me that there's a probability associated with an uncertain future numerical outcome. That is called as a random variable. It is called as a variable because this capital X, when I'm rolling a die, can vary, right? I can either get 1, or it can vary and it can be a 2, or it can vary and it can be a 3, or it can be a 4 or a 5 or a 6. So the outcome varies. Hence it is called as variable, for the only reason that it can take one of the several possible outcomes which are listed down here. And it is called as random because there is a chance associated with each possible outcome. For example, what is the probability that I get a 1 if I roll a dice? 1 by 6. What is the probability that I get a 2? 1 by 6. 3, 1 by 6. So for each and everything, there is a 1 by 6 chance. I'm not telling for certain that I'm 100% sure that there would be 1 until unless you bias the dice in some way. That would not happen. Hence it's called as random variable. It's random because it is having an uncertainty attached with that, and it is variable because it can take any of the possible outcomes. Then what is a probability distribution? Probability distribution is a long run average of a random event occurring. Let me follow up this with a series of questions. If I toss a coin once, you have told me that there is a probability that I'll get a head once. Sorry, there's a 50% chance that I might get head. What if I toss a coin twice? What would be the probability associated with that? What is the probability of getting a head if I toss a coin twice? Only Enoch has responded. Oh, Monica also has responded. No one else has responded. What happened? Aditya has responded as 1 by 4. Absolutely. The probability associated with that is, say I'm flipping a coin once. What is the probability associated with it? 50% or half. Say I'm tossing a coin twice. What is the probability associated with that? Half. So it's 1 by 4. What if I toss a coin thrice? 1 by 8. What if I toss a coin a million times? What if I toss a coin a trillion times? What if I toss a coin 999 times? What if I toss a coin 1999 times? Or 10,000 times? Or 50,000 times? Or 28,000 times? All that, all those possible things, right? Yeah, all those possible probabilities, if I plot it on a graph, it would look like this. Right? And if you do an experiment, in reality, if you go ahead and do an experiment a million times or a billion times or a trillion times and try to plot that against the number of times you're trying to um, toss the coin and the number of heads you're getting, it would follow this distribution only. You can try it out. And whatever probability that you have told will more or less hold good only and only if you perform many experiments. Only and only if you perform many experiments. Let me quickly ask you this. Right? You have told me that if I flip a coin twice, there is a 1 by 4 probability to get ahead. That means you're telling that there's a 25% probability that I'll get ahead, right? Just try out on your own and see whether you're going to get 1 head or 2 heads or 3 heads or 4 heads or 0 heads. Just try that experiment on your own. It will never be 1 by 4. I mean, very rarely it's gonna be 1 by 4, right? If you keep flipping a coin, or if you flip a coin 4 times, are you telling me that 100% I would get 1 head and 3 tails? Would that be possible? When I ask you on what is the probability that I'm going to get a head if I toss a coin once, you told 50%, twice 1 by 4. So I'm asking you this, instead of twice, right, just extend it. Flip a coin 4 times and check how many times you're going to get a head. It will not be in line with whatever probability you're giving. Even if you take example of flipping a coin twice and the associated probability is 1 by 4, flip a coin twice and check it for your own, right? So don't take in the literal sense, but if you perform an experiment of flipping a coin 1,000,000 times, 1,000,000,000,000 times, and if you try to plot it, it would appear in this format. It would be normal. And this is called as probability distribution. All the possible values which an experiment can take would fall under this normal distribution. And we have yesterday discussed about what is discrete data and what is continuous data. Do you guys remember the difference between discrete and continuous distributions? Data types. Do you all understand the difference between discrete and continuous data? Except for Monica, no one else has responded. Do you want me to explain once again, or do you know the difference between discrete and continuous? All right. So do not worry much about this probability distribution. We'll do a lot of exercises on that and things would become a little clear for you. Okay, take this simple example. Suppose you have randomly picked a card from a card deck. What is the probability that this card will be bigger than 10? What do you guys think? Enoch says number of cards minus 10 divided by total cards. Sure, Enoch? How many cards would you have? Question is different, right? What is the question that I've asked? Yes, 52. Look at that. How many playing cards would be greater than 10? You would have J, Q, and K, Jack, Queen, and King, right? You'll have only 3. How many colors and variety of cards do we have in Jack? We have 4, right? 2 red and 2 black. And how many cards would you have of Queen? 4. How many cards would you have for King? 4. So it'll be 4 plus 4 plus 4, which is 12. out of total 32 cards. Is this clear? Probability of getting a card which is bigger than 10 is 12 by 52. Let us understand this second thing. What is the probability that the card that I'm going to draw randomly from a card deck would be equal to or bigger than 10? Monica and Enoch has responded. How about our other friends? Aditya, Sudipto, Vijay, what do you guys think? All right, let me quickly explain this to you all. Right. Greater than or equal to, sorry, greater than or equal to 10, right? So I need to include 10, J, Q, and K. These are the cards which are greater than or equal to 10. You will have 4 different 10 cards, 4 different J, Jack, 4 different Queen, and 4 different King cards. How many total cards are there here? 16, right? 16 out of total cards would be 52 in a deck. So that is a probability that if I pick a card randomly from a card deck of 52, this is a probability that I'll get a number which is greater than or equal to 10. Please calculate and tell me what would this number be, smaller than 3. Eight by 52. Anyone? A would be 1, Enoch. Oh, don't you guys play cards? Never? This is surprising. No? Is it dignity or lack of opportunity? All right. So let me explain you quickly about this. Oh, you have played in your 10th math class. All right. There's nothing wrong in playing cards, right? James Bond does that. Now, by the way, there is a movie about to be released. Okay. Smaller than 3. How many numbers would be smaller than 3 in your playing cards? 1 and 2, right? There are only 2. You would have 4 different varieties of A and 4 different varieties of 2. And 1 is nothing but A within the playing cards. So you have 8 in total. 8 out of 52 cards. This is the probability that if I draw a card from the playing card, I would get a number which is less than 3. Can you all try to find this? Greater than 4 and less than 8. Yeah. Yeah, you guys are right. How many numbers would I have in between 4 and 8? 5, 6, and 7, right? Each card will have 4 varieties. Diamond, spade, flower, and heart. Those are the 4 types, right? So it's 12 divided by 52. There's a probability associated with this. Whatever we have discussed in the previous slide about probability distribution, let us quickly understand here also. Suppose we have data sales of large flat panel television set at a store, and I have this X, right? Capital X. So what is the probability that there will be 0 television sold on a particular day? It's 0.4. What is the probability that 1 television set would be sold? 25% or 0.25. What is the probability that there would be 2 television sets which would be sold? It's 20% or 0.20. What is the probability that I'm going to sell 3 television sets? 5%. What is the probability that 4 television sets will get sold? It's 0.1%. Now if I plot the same thing in this way, this is nothing but my probability distribution. Since we have only 4 possibilities, it's appearing in that way. What if I have a million opportunities or a million television sets, and the probability associated with all of those million television sets is available? How would the distribution look like? There will be many bars in the given region, right? There'll be a lot of small bars, a lot of thin bars. And if I fit in a million here, it would obviously look like a continuous distribution. It will be very continuous, right? There won't be so much of gap. Since there are only 4, they are neatly segregated. But what if I have a million, and what if I want to put in all the million entries in this given space? It would appear continuous in that way. All right. Please answer these 2 questions. What is the probability of a sale happening in this particular store? Monica says 0.6. Do you all agree with her? Not sure. When do you say that there is a sale? When do you say that there is a sale? When if 1 television set is sold, or 2 or 3 or 4, right? At least 1. So this 0 you're going to strike off. And we have a probability. Yeah. Final conversion means, Sudipto, someone is purchasing, right? And that is the data which is provided here. And I'm asking you to tell me the probability, not the reality. Probability. Probability of having a sale is either selling 1 television, 2 or 3 or 4 television sets. Given this data, I'm going to simply sum up all these probabilities. So it'll be 0.25. That is a probability that 1 television set might be sold, plus 0.20. This is the probability that 2 television sets might be sold, plus the probability that there will be 3 television sets sold is 0.05, plus probability of 4 television sets being sold is 0.10. If you sum up, the total would be 0.6. Or simply speaking, I would say, hey, it's 1 minus 0.4. Always the probability of all the events within a given scenario would be equal to 1. If you sum up this entire thing, it would come up to 1. whatever experiment you deal with, the sum of all the possible events, probabilities associated with all the events occurring would always be 1. So either I can subtract 1 from no sale happening, that means that's the probability associated with some sale. Okay, if you guys have any doubts whatsoever, ask me. These are the basics. If you have doubts with the basics, you'll not be able to grasp the advanced concepts. All right. What is the probability of selling at least 3 television sets? All right. At least 3 means greater than or equal to 3 television sets. Probability of selling 3 television sets is 0.05. Probability of selling 4 television sets is 0.1. So if I add these two, it will be 0.15. Clear, or do you guys have any doubts in this? Vijay, is this clear? Rajiv, you also can ask me if you have any doubts. Clear? All right. Great. Okay, let us move on to the next thing. Now